Ever heard that phrase, the universe is written in the language of mathematics?
Mm-hmm.
Galileo said it.
Yeah.
It's one of those that makes you realize just how fundamental numbers are to, well, everything.
Right.
And that's what we're diving into today, quantitative research. We're talking surveys, stats, all those ways we wrangle data to make sense of the world.
And you know what? It's not just about complex equations or anything like that.
Right.
I mean, we use quantitative research all the time, probably without even realizing.
Oh, absolutely.
Think about it. Election polls, built on crunching numbers.
For sure, yeah.
Clinical trials, testing a new medication. Quantitative research again.
It's everywhere. It really is. And today, our guide is a document called simply Quantitative Methods. Our mission, should we choose to accept it, is to give you a solid understanding of how it all works, what its strengths and weaknesses are, and why it matters to you, even if you don't consider yourself a numbers person.
Right.
You ready to unlock the power of numbers?
Absolutely. Let's dive in.
So before we get into the nitty-gritty, let's talk about the difference between quantitative and qualitative research.
Okay.
Sometimes they're seen as opposites. It's not really accurate, is it?
No, not at all. They're more like two sides of the same coin, each giving us a different perspective on the same issue.
Okay.
Think of it this way. Qualitative research is like having a long, in-depth conversation to really understand someone's experiences and motivations. Quantitative research, on the other hand, is like looking at a map of their journey.
Okay.
It shows you the overall path, the patterns, but not necessarily the emotional details of each step.
Okay, that's a really helpful way to visualize it.
Yeah.
So if we were trying to understand something like consumer behavior,
Okay, yeah.
qualitative research would be about those in-depth interviews, really getting into the why behind people's shopping habits.
Right. But the quantitative approach might analyze credit card data,
Fascinating.
looking at spending patterns across different demographics.
Yeah, that makes sense.
In fact, one of the insights you might find is that, and this probably won't come as a surprise to many, is that household consumption grows with revenue.
Logical. But proving it with data is key, which brings us to a really important concept in quantitative research. Indicators. What makes a good indicator anyway?
So think of an indicator like a signal fire.
Okay.
It's supposed to draw your attention to something important.
Right.
A good one needs to be relevant to what you're actually studying.
Okay.
Useful in the sense that it provides meaningful information and easily understood by anyone looking at the data.
So not just any old number will do.
Exactly. Take, for example, measuring educational outcomes. You could look at high school graduation rates. That's relevant. That's measurable.
It is, yeah.
You could even compare these rates between different regions, say between Reunion Island and mainland France.
Okay.
And understand regional differences.
Yeah.
But you also want to consider if that indicator tells the whole story.
Right.
Does it account for students who drop out but later get their GED?
That's a good point, yeah.
Yeah.
So even when it comes to seemingly straightforward numbers, critical thinking is key.
It is.
Speaking of which, let's dive into some statistical concepts that are essential for making sense of all this data.
Okay.
Don't worry, we'll keep it jargon-free.
Yeah.
One of the first things they teach you in stats class is the idea of the average. But there are actually a few ways to calculate that, right?
Absolutely. So we have the mean, which is what most people think of when they hear average. Add up all the values, divide by the number of values.
Right.
But then there's the median, which is the middle value when you arrange all the values from lowest to highest.
Okay.
And finally, there's the mode, which is the most frequent value.
Right.
Each one tells you something a little bit different about the center of your data.
So depending on the data, using the wrong average could really skew your interpretation.
Absolutely.
Right.
Then we've got measures of dispersion.
Okay.
Things like standard deviation and quartiles. These tell us how spread out the data is.
Okay.
Imagine you're looking at salaries in two different companies. They both have the same average salary, but one has a much larger standard deviation. That tells you there's more variation in the individual salaries.
Okay.
Some people might be making a lot more, while others are making a lot less, even though the average is exactly the same.
Got it. So understanding these different measures helps us paint a more complete picture, not just fixating on one number. Now let's talk about probability.
Okay.
Something I think trips a lot of people up, including me sometimes.
Yeah, it can be counterintuitive, that's for sure. Let's say you have a medical test that's 99% accurate at detecting a particular disease.
Oh.
You take the test and it comes back positive. Most people would assume there's a 99% chance they have the disease, right?
Yeah, That seems like a logical conclusion.
But that's not always the case.
Really?
That's where conditional probability and something called Bayes' theorem comes in.
Okay.
The actual probability depends on other factors too, like how common the disease is in the general population.
Oh, okay.
A positive test result doesn't definitively mean you have the disease. It just increases the probability.
Wow. That's a really important nuance. It reminds me of that saying, correlation doesn't equal causation. Just because two things happen together doesn't mean one causes the other.
Exactly. There's a website called Tyler Vigen's Spurious Correlations that hilariously illustrates this point. You'll find graphs showing strong correlations between things like the number of Nicolas Cage films released and the number of people who drowned by falling into a pool.
Okay, that's amazing, and a great reminder that we can't just blindly trust statistics.
No.
We need to understand the context and look at the bigger picture. But before we go there, I'm curious to dig a little deeper into the different types of statistical tests.
Okay.
What are some of the most common ones that researchers use, and how do they decide which one is right for their study?
Well, there's a lot of different tests, each designed to answer specific types of questions about the data.
Like different tools in a toolbox?
Exactly.
Okay.
For example, you might use a t-test to compare the average height of men and women, or a chi-squared test to see if there's a relationship between smoking and lung cancer.
Right.
Choosing the right test depends on factors like the type of data you have, the research question you're asking, and the assumptions you're making about your data.
So there's no one-size-fits-all approach to statistical analysis. It's about selecting the right tool for the job.
Precisely.
This is really fascinating stuff. Now, I know we can't analyze data from an entire population.
Okay.
That's where sampling comes in.
You got it.
Yeah.
Sampling is all about choosing a smaller representative group from a larger population to make inferences about the whole. It's like tasting a spoonful of soup to get a sense of the entire pot.
Right.
If you stir the pot well and take a spoonful from the middle, you'll get a pretty good idea of what it tastes like without having to eat the whole thing.
Makes sense. But how do researchers make sure those spoonfuls, the samples they choose, are truly representative of the whole pot of data?
That's where sampling techniques come in,
Okay.
which we can explore in detail after a quick break.
So we're back and ready to dive into those sampling techniques, those clever ways researchers create those representative spoonfuls of data.
Exactly. And one of the most important distinctions to understand is the difference between probabilistic and non-probabilistic sampling.
Okay.
Probabilistic sampling is all about randomness,
Okay.
giving every member of the population an equal chance of being included in the sample.
Sounds fair. Kind of like picking names out of a hat.
You got it, but often with a bit more sophistication. Simple random sampling is the most basic form. Imagine using a random number generator to select participants from a list. Then there's stratified random sampling. This is used when you want to ensure representation from specific subgroups within the population. For example, if you're studying voting patterns and want to make sure you have proportional representation of different age groups, you'd use stratified sampling.
Makes sense. Divide the population into those subgroups, then randomly select from each. So it's still random, but with an extra layer of control to make sure the sample reflects the overall population's makeup. What are some other techniques researchers might use?
Well, there's cluster sampling, which is especially useful when you're dealing with large geographically dispersed populations.
Oh.
Imagine you're studying school performance in a particular state. Instead of trying to randomly select students from every single school, you could randomly select a number of schools and include all of the students from those schools in your sample.
That's much more efficient than trying to collect data from hundreds of schools.
Exactly. And lastly, there's systematic sampling, where you select every nth individual from a list.
Okay.
It's a structured approach that ensures even coverage across the population.
So lots of options when it comes to probabilistic sampling, all about that element of randomness. What about non-probabilistic sampling then? When might researchers choose to go that route?
So non-probabilistic sampling is used when random selection isn't feasible or when the goal of the research is different. One common type is convenience sampling, which is exactly what it sounds like, selecting participants who are readily available or easy to reach.
Right.
This is often used in pilot studies or exploratory research where the goal is to get some initial insights quickly.
Okay, so maybe not the most representative, but useful in certain situations. What are some other non-probabilistic methods?
There's purposive sampling, where researchers handpick participants based on specific criteria or characteristics that are relevant to the research question.
Okay.
This is common in qualitative research where you want in-depth understanding from particular individuals or cases.
Got it. So if you were studying, say, the experiences of Olympic athletes, you might use purposive sampling to select athletes from a variety of sports and backgrounds.
Exactly. And then there's quota sampling, which aims to create a sample that reflects the proportions of different subgroups in the population.
Okay.
Similar to stratified sampling, but without the random selection.
So you might set quotas for the number of men and women, or different age groups, to ensure some level of representation.
Right, but it's important to remember that non-probabilistic samples might not be generalizable to the larger population. The choice of which sampling method to use depends on the research question, the resources available, and the ethical considerations involved.
It's all about making strategic decisions to get the most meaningful data possible. Now that we've talked about collecting data, let's go back to analyzing it. We touched on statistical tests earlier, but I think it's worth diving in a little deeper.
All right.
Let's start with something called a QQ plot.
Okay.
It sounds a bit technical. What's it all about?
Don't let the name intimidate you. A QQ plot, short for a quantile plot, is a visual tool that helps us determine if our data fits certain patterns.
Okay.
It helps answer the question, does our data look like it comes from a normal distribution? That bell-shaped curve we often see.
So like checking if the data points line up in a certain way.
Exactly. Imagine you're looking at the heights of a group of people. If you plot that data on a QQ plot and the points roughly form a straight line, it suggests that the heights are normally distributed. Most people are clustered around the average height with fewer people at the extremes. But if the points stray from that line, it could indicate a different type of distribution, and that can impact what kind of statistical tests you use.
It's like a quick visual check to see if our data is playing by the rules, statistically speaking. Okay, how about another test? I hear there's one literally named after a brewer.
You're thinking of the D-test, developed by William Seeley Gossett, who worked at the Guinness Brewery.
No way. I love that there's a statistical test with a beer connection. What does the D-test tell us?
It's a very common test used to determine if there's a significant difference between the means or averages of two groups.
So, like comparing the average height of men and women, or the average test scores of students who did or didn't get extra tutoring.
Exactly, and there are variations of the test depending on the type of comparison you're making. Comparing a single group to a known value, comparing two independent groups, or comparing the same group before and after some intervention.
So it's a versatile tool for comparing those all-important averages. What if the data isn't as straightforward, though? What if we're looking at things that aren't easily measured on a numerical scale, like opinions or rankings?
That's where non-parametric tests come in handy.
Okay.
One example is the Wilcoxon test, actually a couple of related tests named after Frank Wilcoxon.
Okay.
They come in handy when the data doesn't meet the assumptions of a t-test, like having a normal distribution.
It's like having a backup plan for when the data throws you a curveball.
Exactly. And then there's linear regression, which is used to analyze the relationship between two continuous variables, things you can measure on a scale.
Oh.
Imagine plotting data points on a graph. Linear regression helps us find the line that best fits that scatter of points.
So if we were looking at the relationship between hours of study and exam scores, linear regression could tell us if there's a correlation and how strong it is.
Precisely. The steeper the line, the stronger the relationship. But, and this is crucial, even if we find a correlation, it doesn't necessarily mean one thing causes the other.
Right. Correlation isn't causation. We might see a correlation between ice cream sales and drownings, but it doesn't mean ice cream is causing people to drown. There's probably another factor at play, like hot weather.
Exactly. Now, shifting gears a bit, we have the chi-squared test, which is used to analyze categorical data.
Okay, so instead of numbers on a scale, this is about categories. Like comparing preferences for different types of music, or maybe looking at whether there's a relationship between gender and car ownership.
You got it. The chi-squared test helps us determine if there's a statistically significant association between two categorical variables.
It's amazing how many different statistical tools are out there, but it sounds like choosing the right test is crucial, like trying to bake a cake with a hammer instead of a whisk.
That's a great analogy. And speaking of choosing the right tools, let's talk about the importance of understanding statistical significance.
Okay.
Because I know that's a phrase we hear a lot, statistically significant. But what does it actually mean? And what about effect size? That seems important too, right?
It does, yeah.
Absolutely. We often hear about statistically significant results, but that term can be misleading. Essentially, it tells us whether the results we observed in our sample are likely due to a real effect or just random chance.
So like trying to figure out if our findings are actually meaningful or just a fluke.
Precisely. The p-value is a key concept here.
Yeah.
A small p-value, typically less than 0.05, suggests that the results are statistically significant. However, statistical significance doesn't always equate to practical significance. That's where effect size comes in. It tells us the magnitude of the effect we observed.
So a statistically significant result with a small effect size might not be all that interesting in the real world.
Exactly. For instance, a study might find a statistically significant difference in test scores between two groups of students. But if the effect size is tiny, the difference might be negligible in practical terms. It's like saying you found a statistically significant difference in height between two groups of trees, but the difference is only half an inch. Not exactly groundbreaking.
Right. It's about putting those findings into context.
And that's where confidence intervals come in. They give us a range of values within which we can be reasonably confident that the true population parameter lies.
Okay.
It's a way of acknowledging the uncertainty inherent in statistical estimates.
So instead of just getting one number, we get a range, which reflects the fact that we're working with samples, not the entire population.
Precisely. It's like saying, we're pretty sure the true average height of people in the city falls somewhere between 5'4" and 5'6". We can't say for certain what the exact average is, but we're confident it's within that range.
Confidence intervals, a good reminder that statistics is all about probabilities, not absolutes. This has been a really fascinating dive into the world of statistical analysis. It's amazing how much thought and consideration goes into choosing the right tools and techniques.
It's all about asking the right questions, carefully designing studies, and interpreting the data responsibly. And sometimes that involves stepping back and considering the ethical implications of our research.
That's a really important point. It's not just about the numbers. There are real human beings behind those data points, and it's crucial to treat their information with respect and sensitivity.
Right.
What are some of the key ethical considerations researchers need to keep in mind? It's really easy to get caught up in the technical details.
It is.
But at the end of the day,
Yeah.
research is about people.
Precisely. We always need to consider the potential impact of our research on individuals and communities.
Right.
For example, are we collecting data in a way that respects people's privacy and confidentiality?
Right.
Are we being transparent about how the data will be used?
Good point.
These are questions that researchers should be asking themselves at every stage of the process.
It's about using these powerful tools responsibly.
Right.
Speaking of which, we've covered a lot of ground in this deep dive.
We have.
From basic definitions
Yeah.
to some pretty nuanced statistical concepts.
Yeah.
What are some key takeaways you hope our listeners will walk away with?
Well, I hope they've gained a deeper appreciation for just how much quantitative research goes on behind the scenes.
Right.
It's how we make sense of everything from election results to the effectiveness of new medications. And even though it might seem intimidating at first, the basic principles are surprisingly accessible once you break them down.
Right. It's not just for statisticians in ivory towers.
No.
And as we've discussed, it's not enough to just glance at the numbers.
Right.
We need to understand the context, ask critical questions, and be wary of potential biases.
Exactly. Think about those spurious correlations we talked about earlier.
Right.
Just because two things are correlated doesn't mean one causes the other. We need to be savvy consumers of information, especially in today's data-driven world.
So it's about asking those critical questions.
Yeah.
How was this data collected?
Right.
Who are the participants?
Yeah.
What statistical tests were used? And what might be missing from the picture?
You got it. And don't be afraid to dig deeper, to
Yeah.
look for the original research study, rather than just relying on a news article or a social media post.
It's like being a data detective,
Yes.
following the trail of evidence, asking tough questions to uncover the truth.
I love it.
This deep dive has really highlighted that quantitative research isn't just about crunching numbers. It's a journey of discovery,
It is.
a way of unraveling the complexities of the world around us.
Absolutely. It's about using the power of numbers to illuminate hidden patterns, test our assumptions, and ultimately gain a deeper understanding of ourselves and the universe we inhabit.
Wow. So well said.
Yeah.
We've talked about the tools and techniques, the importance of critical thinking, and the ethical considerations that should guide all research.
Right.
But as we wrap up this deep dive, I think it's worth reiterating that even with the most sophisticated statistical analysis,
Yes.
there's always an element of human judgment involved.
That's a really important point. We can't just blindly follow the numbers.
Right.
We need to consider the context, the limitations of the data, and the potential implications of our findings.
It's about using our knowledge wisely and responsibly,
Yes.
recognizing that behind every data point,
Yeah.
every statistic, there are human stories that deserve our attention and respect.
Well said. Quantitative research has the power to inform our decisions, shape our policies, and ultimately create a better future.
Yeah.
But that power comes with the responsibility to use it ethically, thoughtfully, and with a deep respect for the complexities of human experience.
On that note, it's time for us to wrap up this deep dive into the world of quantitative research. We hope you've enjoyed the journey and come away with a renewed appreciation for the power and the responsibility
Right.
that comes with unlocking the secrets hidden within data.
Until next time,
Yeah.
keep those critical thinking skills sharp
Yes.
and never underestimate the power of a well-placed question.
So true. Thanks for joining me.
Thank you for having me.